Hi, everyone. We're getting close to the top of the hour. Welcome to Radiation Hardening and Spacecraft Charging, an EMA Expo 2025 event. My name is Jason DiMartino, and I'll be your host for today's presentation. We're aiming to run around 90 minutes with a half hour for questions at the end. So please be advised that to submit any questions you have during the webinar, you can use the Teams webinar Q&A feature, and after the presentation, we'll address any submitted questions. Should there be any unanswered questions at the end, we'll address them over email. Our speakers today are going to be Kevin Miranda and Colin Brennan. Kevin Miranda is a Principal Scientist 1 at EMA, Electromagnetic Applications, and, the Software Product Manager of Ansys Charge Plus, formerly EMA 3D Charge. Kevin received his Master's in Physics at École Polytechnique Fédérale de Lausanne in Switzerland, and his PhD in physics at the Colorado School of Mines. Kevin joined EMA in 2020 to apply his expertise to computational physics, atmospheric electricity physics, and elementary particle physics to impactful industry projects. As it turns out, his technical proficiency and communication skills were also ideal for the role of product manager. Since starting at EMA, Kevin has developed mastery in the fields of spacecraft charging, radiation hardening, electrostatic discharge, and magnetohydrodynamics. Kevin has given multiple talks on these topics and on the current and future capabilities of Ansys Charge Plus in the space and defense, electronics, semiconductor, electrical equipment, electric power, and automotive industries. Colin Brennan, who will be our second presenter, is a staff software developer at EMA, where he develops software and methods for performing radiation hardening analysis in Ansys Charge Plus. Currently, he's developing the ray tracing dose estimation tool in Charge Plus, which uses 3D CAD and video optics and coupling with Ansys STK to produce estimated dose maps on sensitive electronics and space platforms. He received his BS in physics with a concentration in radiation physics from the University of Texas at Austin. He's finishing a MS in mechanical engineering with a concentration in computational nuclear engineering, also from UT. His research involved developing a novel acceleration scheme for eigenvalue neutron transport problems. His technical interests include finite element methods, radiation transport, multiphysics modeling, and simulation and machine learning for engineering analysis. Without further delay, I give you Kevin.
Thank you for the introductions. Good to have everyone here today. We're very excited to show you all the new technology that we have in the tool and how to leverage it the best possible for your various applications. The title of the workshop is Radiation Hardening and Spacecraft Charging. We're going to touch a little bit on deep dielectric charging using high energy particles. And we'll do a big focus on our updates to the radiation hardening capabilities within Charge Plus and how to use the new tools and the new capabilities that we have inside the software. So I kind of refined the title a little bit to focus on radiation hardening. That will be the workshop today. But I'll talk about kind of the tool in general and how things came to be related to radiation hardening specifically. So I also have a quick introduction to space radiation environments, and this will be a bit of a repeat to the session this afternoon. So I will go very quick over this concept just to introduce the context of what we're doing here today. But please attend the session later today that is more focused on deep details on what radiation environments is and how testing and simulation relates to these aspects. So space radiation comes from various different sources. The radiation hardening that we're talking about could come from space radiation, but might as well also come from nuclear reactors or fusion reactors and other types of devices that could create some high level of radiation. But in space, it's just naturally there. The sources come from the sun, the Earth, or the galaxy. And typically, depending on where they're coming from, the energy is going to be different, and the effects on the electronics and the devices is also going to be different. And so we need to have all the tools possible to be able to address all the different energy and particle types that are out there in space. So space radiation, we're really focused on solar energic particles. And again, I think we'll get a lot more details on all of these later on, so I'm going to go through this pretty quickly. But we're looking at energies that are on the order of keV to over 500 MeV, and that's enough for these particles to be able to penetrate deep inside dielectrics and to create some upsets of electronics. To understand what ionizing dose is going to be there is very critical, because these can have long-term damage effects to the devices. And if you look at the lower energy parts of these radiation environments, you'll see that you're going to have more effects related to surface charging. And we also have tools for that inside Charge Plus, but that is a whole different workshop and discussion. There's obviously electromagnetic radiation, both in UV lights, but also electromagnetic pulses and things like that that could be in space and affect the system. Here we're focused more on energetic particles than we are on electromagnetic radiation. There's also radiation from trapped radiation belts and from atmospheric particles. These typically have a lower energy component, and this is where surface charging is a problem, so not a big concern for today's discussion. One that is very important for today's discussion is space radiation, things that come from within the galaxies that, or even outside the galaxy, so cosmic rays. These have very high energies, and they are more than just electrons and protons. They are ions that can actually go and penetrate through a whole system and deposit charge behind them, or even just really create a pretty drastic upset within the electronics. Being able to model this is important. And then we also have various anomalous cosmic rays that are discussed here that are from sources that are a little closer and that we have to consider, but they may be slightly slightly lower in energy than the galactic cosmic rays. Obviously, there is environment of charge that is building up around a satellite that may need to be considered. This can be effects from just the surface potential or the reaction of these particles with the surface of the materials, propulsion systems, outgassing materials from electronic boxes, things like that. But for the sake of radiation hardening, these may not be as critical. They are very critical for the surface charging aspects and maybe sputtering effects on the solar arrays. But the key is to understand and differentiate what kind of environments we care for when we're looking at radiation hardening and deep dielectric charging versus what we care for when we're looking at surface charging and the risk of ESD. And so understanding these environments is key. And I think this is the type of contributions that may not be as relevant for looking at rad-hard specifically. So I want to stress that ground-based testing is always important, even for ionizing dose, deep dielectric charging, and because sometimes there are types of tests that are critical, like looking at ion beams on devices and getting upset rates for various devices. There's a lot of standardized methods for testing that are out there that are present. EMA is very familiar with doing these tests, and we use these tests to also validate our simulation. It is something that we really think that is pretty critical. So one of the other key things of these tests is understanding the characterization of the materials. Material properties are key, so conductivity, dielectric properties, and even more fundamental cross-section data for the materials is important to make sure that we can also help the accuracy of simulations. A lot of risk mitigation and component and system level testing is done through big testing campaigns, and I think those are also very critical to the missions to make sure that devices are reliable and safe. There is a cost effectiveness to testing. We know that if we do it in a very specific way, we can assure a certain safety standard, we can comply with regulatory demands, and there's various development strategies that can be done for mitigating the consequences of some of the testing that we have. So enhancing reliability is key, but it is costly in some way to try to change the design and go back to a test campaign and shine some more particles onto the system and understand how radiation hardening needs to be mitigated. So that's where I think simulation can become very handy, right? So instead of having testing campaigns of the order of $500,000, we may be able to just do simulation campaigns for $50,000. And that helps us significantly really refine the testing cost of these campaigns and making sure the device can become reliable quickly. So the key to simulation is that we don't have any limitations on the sample size. We're not destroying the device. We can shine any particles that may be very hard to access in a test facility. Maybe some test facilities don't even have the radiation environment that you need to be able to test for. Simulation really helps you run all these different types of exposures to long duration, short duration, electromagnetic effects, photons, things like that. And so understanding these makes simulation very powerful. The other thing that's pretty critical is that simulation and testing and these type of kind of safety procedures have to be done earlier on, right? Obviously, it's too late when things are in space. We have to do these simulations and risk mitigation techniques early in the design process. And so in some cases, simulation is used as a diagnostics tool to understand why a problem occurs. But we always want to make sure that we also use it at the design level to make sure that we don't get any problems in the first place. And so this diagram is really showing some of the techniques and tools and problems that we can solve with Ansys Charge Plus, the tool that we'll talk about today. We do the surface charging analysis, so choosing materials at the surface of the satellite is key for those low energy component space environments. And then we can also model the charging of dielectrics like solar arrays and the discharging. So this could actually help us size the TVS diodes that would be needed from one solar array to the main chassis. And then even going further, we can look at doing ESD testing of PCB components within the spacecraft. So this is important if some maybe astronaut is static charged and is touching some of the devices and wants to understand and want to make sure that they're not actually have any issues under ESDs and things like that. So there's a lot that the tool can do to help us out solve some of our concerns. You're probably by this time already very familiar with our partnership with Ansys. Our two tools are distributed through Ansys EMC Plus and Ansys Charge Plus. Ansys Charge Plus is the tool that's really focused on doing this multi-physics of high energy radiation and coupling that to an electromagnetic solver if needed. And this is where the concept of spacecraft charging comes in, right? So we can model the elementary particle physics associated to that high energy space environment, but then we can also couple it to electromagnetics to understand the consequences of that higher energy radiation with various components like electronic devices or things like that or currents on cables and fields build up in enclosures that are exposed to various radiation environments. And so being able to have that coupling is key, and this is what the tool was developed for. One of the things that we really wanted to do is because of our very powerful integration with this elementary particle physics, we worked very hard at disentangling the FEM and the elementary particle physics so that users can run radiation hardening simulations without having to handle the overhead of the electromagnetic solver as well. So even though it's still there as of 25R1 and 25R2 this year, you're now really able to run the radiation transport code on its own independently from the electromagnetic solver. And that helps us not have as simplified of geometry, as cleaned up meshes, things like that. We have ways to create, as you'll see today, meshes very efficiently and be able to run the radiation transport on much more complex geometries that maybe we were able to do in the past. So it is a multi-physics solution. You'll find Ansys Charge Plus inside the Discovery tool. you'll see that we have all the tools for prepping the geometry, which is really very important when you get a CAD from your mechanical team. You want to be able to use that quickly, assign materials. All this is doable in the tool, but then also prepping it for simulation is key. And we, by partnering with Discovery here and having our tool within Discovery, we're really able to leverage that technology efficiently. And some of the cleaning up tools are very mind-blowing and speed up the workflows tremendously in terms of getting simulations ready to go for rad-hard analyses. And then you go and navigate to the Charge tab, and there you get access to being able to set up many different types of simulations. We have, as you'll see today, the ability to just select the rad-hard simulation workflow, and that will really streamline and run the radiation transport code on its own with the new probes that we have incorporated inside the tool. As always, we have documentation available. We're working very hard to make sure that all the overlay help that you get using F1 are updated and very useful for this latest release, especially with all the new tools that are coming. We want to make sure that we provide all the help that is needed for you to take on the tool and learn the tool on your own. There is a lot in Ansys Charge Plus, so even though you may be using the tool specifically for rad-hard, just keep in mind that there's a lot of other technology inside the tool, and rad-hard problems can become as hard as you want to make them, right? So if you try to understand how, for example, a photon pulse from terrestrial gamma ray flashes of lightning, for example, interacts with an enclosure on a spacecraft, it's going to be much more complicated than just running a pulse of photons from that TGF. It's going to be coming from, there's going to be aspects of it that are going to create electromagnetic fields. There's going to be gases in your electronics box that you may be considering, because there's plasma forming around the box and inside the box that is redistributing itself based on the fields within imparted by the box, and that will change the whole charging aspect of the components within the box. And so being able to think of various ways to couple all this physics together is important. It's not easy, but it is doable, right? So we have the ability to model nitrogen ionized inside the box at very low pressures using a particle in cell system. And we can even model degassing. We can model even drag effects using this PIC solver. And then from there, we couple it with the electromagnetic solver so that if there are fields generated by the plasma, we can capture those. And then at the same time, we can get the fields from the Monte Carlo transport. So there's a lot to consider here. We even have a circuit solver as well to be able to tie into the electromagnetic solver. Today, we'll be focused on how to show you how to demonstrate how to use the Monte Carlo particle transport code. We'll call it MC transport here. And then also the ray tracing shielding analysis solver that we have for those calculations. They work very well together, hand in hand. There is a way to use one tool to feed into the other tool, as you'll see today, and as Colin will be demonstrating. And there's also a lot of synergy to understand which one to use and when, right? And that's what we're trying to achieve today is why would you use full Monte Carlo physics instead of ray tracing to be able to solve these problems? And you'll see today that we'll be able to explain that to you with various hands-on applications. First thing I want to talk about is Charge Plus has a lot of different capabilities, and you can kind of classify the workflows in two different buckets. You can think about space environment effect assessment, so really creating a diagnostics on what the environment will create in terms of electromagnetic fields and see if you're at risk of ESD. But we have a lot of tools inside Charge Plus that can also be used to model the discharges themselves. And that allows you to do management of the space environment, not just by adding more shielding, things like that, but you could go all the way to actually modeling the discharge inside the electronic device on the solar arrays and understand the consequences from that discharge happening so that you can maybe accept the fact that you're going to get some discharge and mitigate the problem around the discharge. How long is it lasting? Are we going to get combustion out of it? Is it going to lead to a full failure? If you need to go that far to be able to make some analysis, we can help with charge as well. Not just the simpler, well, it's not even that simple, but not just assessing if the fields are too high. We can go all the way to modeling the event of the damage as well. So let me do a little bit of a deeper dive into the difference between radiation hardening and internal charging in Charge Plus. Okay, so the two tools that we're using for internal charging are FEM, electromagnetics. We have a full wave and a quasi-static solver. Typically for those internal charging problems, we're using the quasi-static solver. And then we have the Monte Carlo transport, which is an interface for G4. Geant4 is a tool that was built at CERN. It is very well vetted. It's got a lot of different packages based on the physics that you want to retain, based on some new acceleration schemes, or even like other things that are present in the tool. And we interface with those packages and can bring them in. And then we provide a full CAD interface to be able to run G4 simulation with all the cleaning tools that we're talking about, with all the meshing capabilities, and all the fundamental physics of the electromagnetic interactions of the particles with the bulk materials are captured in the tool. We can also use G4 for much more advanced ion interactions and ion particles for the galactic cosmic ray spectrum. And this is why it's key, because all the physics of the neutron interactions is also captured inside G4. And so now we have this inside the tool. We have a way to couple that information to the electromagnetic solver. Basically, every track that stops inside the mesh will leave a certain amount of charge behind, and we can seed the electromagnetic solver with that charge at any location in 3D. This is how we can charge up any dielectric. We can understand how many gases, for example, themselves are charging up due to the radiation transport. And there's a lot of powerful things to do. So the way we developed the tool at first was really to focus on this internal charging, because we knew there was a big gap in internal charging analysis. So this is still very fundamental to spacecraft charging. And then ultimately, we realized that a lot of customers are very interested in having a Monte Carlo transport tool just purely for radiation hardening on all this with this beautiful CAD interface. And so that's why we have been able recently to be able to kind of separate both in some way. But the technology for rad-hard at the end of the day is the same one that we use for internal charging. It's just adding an additional layer of electromagnetics on top of it. One thing that's very cool here too is that I'm not sure there is any other tool out there that couples radiation transport with full wave electromagnetics. I know that there are tools with quasi-statics, but when you're dealing with full wave, you can actually start modeling currents generating by a pulse of photons, for example. So back to those terrestrial gamma ray flashes from lightning, the pulse size might be like microsecond, and that will actually lead to a certain current that we can capture on a cable, for example. And that transient is pretty critical to understand if it's going to affect the electronics. So here on the right, you can see that we have kind of a workflow. We have the radiation hardening aspect. We use the radiation transport to shine particles through a shield to a PCB. And then all we get is the ionizing dose. At the end of the day, ionizing dose is just joules per kilo. It's associated with that. We also have total charge deposited at any given location. And so we can apply that to our electromagnetic solver, and we couple it with all the boundary conditions that we can set up with the electromagnetic solver, such as the currents or voltage, or even the circuit solver that we have now. And then we can understand the full electromagnetic distribution of charge within the system. And even if that charge will bleed over time due to the conductivity of a dielectric. And then on the bottom, we can take it to the next level and use some of the additional tools we have in the FEM solver, for example, the stochastic tree model to model discharges in solid dielectric and actually solve for the discharges that are happening from the charging that we got from that environment. For rad-hard specifically, it became important to realize that forward Monte Carlo was not the only way to do rad-hard. There was another tool that is very popular and very necessary to do analyses much quicker, and that is the ray tracing solver, ray tracing sector analysis here that we're talking about. This is doing an analysis, and we'll get a lot more details on how this works from Colin in a second. We are looking at a point on the PCB, and we are shooting rays across the whole geometry to effectively get the total amount of shielding around the system all the way to the space environment. And then we apply what's called a dose depth curve, which is a pre-calculated ionizing dose value as a function of thickness of shielding material. And then once you apply that to the system, we can extract very rapidly the ionizing dose all the way down to any parts of a system. But that dose depth curve needs to be generated in the first place. And this is where Monte Carlo particle physics comes in, because it's very important to capture all the physics of that process. However, there is some assumptions that are made when you create those dose depth curve. First of all, typically it's done with the full aluminum stack-ups, and it's very different when you have materials that have different Z numbers and that are ordered differently as well. The true dose depth curve of a problem might not be exactly what you would have if you were running a full Monte Carlo transport problem. The other thing is the ray tracing sector analysis is totally decoupled from electromagnetics, so you actually would not be able to do any internal charging from there. You do get information about dose depth curve and total amount of shielding, dose and ionizing dose, things like that. It can be used for any types of dose depth curve. It could be non-ionizing dose. It could be done with other types of particles and electrons and protons. As long as you generate that dose depth curve, then you can go ahead and use it for the ray tracing sector analysis. But it is a very quick workflow, and a lot of customers are just provided with those dose depth curve to do the analyses and the rad hardening of the PCB. And this is a method that is very powerful to get that done. So very simple. Let's start with an electronics box. I promise it's going to get a lot more exciting when Colin takes over. But just for concepts, right, on how things are working, radiation hardening versus internal charging. This is a 1 millimeter aluminum shielding box. It has vacuum on the inside, and then it has a PCB board on the inside. Just a simple dielectric slab. In this case, I used PTFE. And the concept is the same based on the different wall sizes, based on the mesh that we're using. Everything that we're about to do is about showing you how radiation works with respect to electromagnetics. So on the left here, we are showing a couple electron tracks, about 1,000 of them, that are shining onto the top of the box. These electrons, they have a certain energy spectrum. With the Monte Carlo technique, we are sampling from that energy spectrum, and we are sampling the spatial distribution of the source, and we're applying this onto the system. So you need enough statistics to be able to get enough correct information at the bottom. This is by principle what Monte Carlo looks like. In this case, this is a 4-hour transit in the radiation belts, and we took the energy spectrum from that environment. And here you're seeing a lot of byproducts from that source. You can see that some of the electrons are stopping directly in the shield. Some of them are creating secondary electrons that are making it all the way to the PCB. And then in blue, you actually have photons that are generated as well. And these photons will themselves have enough energy to create some more complex physics. And you can see that on the right as an additional track. And this will ultimately deposit charge on the box and deposit charge on the PCB. For the radiation purpose, what we really only care about is basically the flux of the particles making it through the box. So you can see on the right, we're looking at flux density in 3D. And we can make this plot because we extract all this information onto a 3D mesh very easily. And this was done with 10 different time steps. So at each time step, you're seeing a different distribution in the flux density due to the Monte Carlo aspect of the problem. So a lot of the particles are stopping at the top. Then you can see a cloud of secondary particles on the inside in blue and purple. And then on the top is a 3D transparent view. And then on the bottom, you have an actual slice cross-section of the whole box with the PCB on the inside. So the PCB even adds an additional layer of screening. You can see that we're not really getting any light blue in the PCB itself. And this is due to the fact that the FR4 in the plastic is there and can do additional screening and absorption of the charge. And you'll see a lot of that in some of what we're going to be showing later in the demo. Ultimately, with the rad-hard capability, we are calculating dose, right? Just joules per kilo. So we know for each event in our Monte Carlo simulation what energy was deposited on the slab. For typical rad-hard analyses, what we really care about is the total dose for that component. Here, it's the total dose for that PCB, but you could have a separate body on the component itself. And that will tell you if you are within those thresholds that you need to match the standards that we have from NASA, for example, about making sure you're below a certain dose for a given environment. And here, this is kind of showing and breaking this up into pieces where we're really looking at each electron events and the secondaries, making it and depositing various levels of energy across the component. And this is the fine details that we can get and that we extract to actually be able to apply charge to our electromagnetic solver. So obviously we can do this to much more advanced geometries. You can add additional shieldings, thin layers, things like that. And based on the photons versus electrons, you're going to have different levels of radiation reaching the components underneath. In this case, we can see electrons are shielded by this slab that we have here in this stack up, while photons are actually making it straight through to the PCB. We have various probes to actually average the information that we just talked about. Instead of having it represented in 3D, you can create a body probe and you can extract that information per body so that you get the actual total dose deposited in the system. So when we go to electromagnetics, now we have to start considering the spacecraft charging aspects of things and the consequences in terms of E-fields. And so as a simple example, we are looking here at a stepped shield. So the thickness of the shield is increasing, and you can see as it's increasing, you're getting less charge deposited inside the dielectric underneath. And here we're setting electromagnetic boundary conditions such that you have a 0-volt ground at the bottom, and then the charge here is deposited inside the dielectric, and we're seeing the fields build up in various parts of the dielectric. This will keep charging, right? This dielectric has a very low conductivity, and so there's no way for that charge to dissipate. And so you may be reaching thresholds that are high enough to create breakdown inside the system. So back to our box, what does it look like over time, right? So here we're looking at the fields building up inside the box due to this radiation depositing at the upper layer of the box. And then we can see the charge density in our electromagnetic solver that is present as well. And so you can see all the negative charge from the electrons and the image charges building up as well based on the grounding scheme that you have. And these fields can actually be coupled back to the radiation transport because the fields themselves might screen the interaction processes within the box. Take this even further in charge, we can now model the with the PIC solver, the gas inside the box. And so if you have some gas that could get ionized due to those fields, which if you look, they're actually very high. We're talking pretty high levels of over like 10 megavolts, 10 to the 6 volts per meter. So there's a lot of fields that can change things pretty dramatically. The time is very long here in this case, right? So you may not have the transients on the PCBs, but there's a lot of things to consider in terms of the consequences on the box. One thing that's important is how do we get these environments? And I'm almost going to pass the baton over to Colin. I'm almost done. Those environments are can be done from standards. There are also databases like Irene and that you can use. But a lot of these tools are already accessible within a product called Ansys SDK, and SDK Seat, specifically one of the modules within the tool. And so we've integrated our tool to be able to read in the energy spectrum of electrons and protons from SDK Seat, which makes it very streamlined of a workflow, as you'll see today, to be able to do that. I will skip this and let Colin show you a live demo of the process. I just want to stress that what we're going to be focusing on today is a comparison between our new ray tracing solver that we released within the last year and the full Monte Carlo. The ray tracing solution is very powerful. It is developed on NVIDIA GPUs only. It's using optics libraries that are made for ray tracing. That's what NVIDIA GPUs are for gaming and ray tracing. And so we can run these simulations as quickly as ever. So it's very exciting of a technology and such a quick and easy way to get ionizing dose on any type of complex geometry. So with all that, I'll hand it over to Colin. Thank you, Colin.
All right, yeah, thank you, Kevin. I think I'll just go ahead, yeah, and bring this onto the screen. Yeah, so I have some live demo material prepared for us to walk through. Um, so to give a bit of an overview, some of this background has already been discussed, but I'm going to give some context into kind of how the space radiation environment can impact uh, engineering design for, in this case, electrical enclosures, and uh, some deep dive into our capabilities in Charge Plus and our upcoming product Shield Plus for assessing radiation shielding and dose for those types of engineering problems. Um, this this half of the workshop is going to be pretty focused on Monte Carlo transport analysis in comparison with our ray tracing capabilities, and with a very narrow focus on some of the improvements that have been made in the past 6 months that will be available in the upcoming release of our software um, for doing this kind of Monte Carlo analysis for much more complex geometries than we've been able to do historically. Which you can see this here on the right. Maybe giving a bit of a spoiler on the model we'll be working with. Um, so just a quick background, not to kind of belabor the point, because it'll be more discussed elsewhere in Expo, but and probably it's a familiar topic to the people in attendance. But space is a very hostile radiation environment. There are cosmic rays that are emitted from distant processes like supernova and things like this that emit very high energy protons and ions that can cause single event failures in electrical components. And then even closer to home, there are solar rays from like coronal mass ejections and solar flares from our sun, emitting protons, alphas, and uh, ions. And then even within orbit, we have charged particle belts that can also produce chronic dose to electrical components within a space platform. And all of these sources of radiation pose significant risk for mission planning and require shielding concerns. Um, we've already discussed surface charging, but the focus that we'll have today is on the cumulative dose impact. So to kind of put some context on the capabilities that we have in Charge Plus for doing radiation analysis, uh, the two main categories are our Monte Carlo transport tool, um, and as Kevin was discussing, this is a tool where we model the propagation of particles. We track the trajectories of those particles and sample microscopic interactions. So that will be things like scattering, ionization. For charged particles, that'll be continuous slowing down, depositing energy along its track. And because this is a statistical method where we create these simulated particles and track them all individually through our design, we have to do a large number of these particles to get a good convergent solution. For very complicated geometry where you may have very small features, this may be on the order of billions of particles. But one of the great advantages with transport is that we get very good recreation of actual physics. There's not much approximation here. We're handling particles as if they're continuous in energy. We're using cross-section data that is continuous in energy. And there's no expectation on the angular dependence of a source. So for example, you could model a very directed beam that you might have in a radiation facility pretty straightforwardly with a Monte Carlo tool. And then here on the right, I have this kind of axis where between a high fidelity simulation method with a longer runtime, as opposed to something with lower fidelity with a quicker runtime, and transport's going to sit on the higher fidelity side of that axis. And then to put in context, our ray tracing analysis option, that's going to sit as more of an approximation tool, but with a much faster feedback loop, a much faster runtime. And the idea is that for isotropic radiation environments like we have in space, we can do a pretty good job of estimating dose by just tracing rays from a point. That might be our sensitive component through our design and compute the total shielding encountered along each of those rays, and then interpolate that into a known curve to get a contribution to dose. And so the question you could ask is, if we can get this dose information by just running Monte Carlo and looking for energy deposition, then why do we need approximation? Why do we need ray tracing? And kind of this axis kind of explains it. Monte Carlo can be pretty expensive to run, especially if you have very small features which you need to collect good statistics in. If you're in a design process where you need to quickly evaluate the impact of certain design changes, you don't want to sit for 24 hours, for example, for a Monte Carlo analysis to run. You'd much rather sit for a few minutes for a ray tracing analysis to run and give you a pretty good idea. And then the other aspect of this is my understanding is there are programmatic requirements for designs where ray tracing analysis is sufficient for satisfying a dose characterization. And so in that case, let's use ray tracing. It's much faster. Kind of the inverse of that question is, if you can get good dose estimates with ray tracing, then why bother waiting for Monte Carlo? I think that's a very good question. Monte Carlo, being a pretty good recreation of the underlying physics, it lets you explore more questions than you can answer with just ray tracing alone. Because we're simulating that particles explicitly, we can tally more than just dose. We can find out things like what is the linear energy transfer in a component? What is the total charge deposition? What is the fluence of particles someplace in the design? And then you can also tally energy spectra. So you can not just answer what is the fluence of particles somewhere, but what is the spectrum of particles that are traveling through some region of space. All of these things are pretty powerful and let you do much more advanced analysis than you can do with just ray tracing alone. And then one of the kind of fundamental limitations with ray tracing is it assumes that a dose contribution along any given direction from your component is just from a straight ahead assumption, which is that dose from that direction is just due to shielding in that direction, which from our understanding of particle physics, that's depending on the particle species, depending on the spectra, that's not a completely terrible assumption. But there are definitely particle types and energy ranges where that's not a very good assumption at all. Monte Carlo is going to do a much better job of capturing higher order effects due to placement of different materials in your design, the geometry, and then physics processes. So Monte Carlo is going to do a much better job of giving you dose contributions from secondary particles that may be generated from, a particle comes in, interacts in one part of your design and creates a secondary particle that then goes on and deposits energy somewhere else. Depending on your design, that may be a pretty significant contribution of dose. And ray tracing is not going to do a good job of giving you that information. Kind of feeding into that, heterogeneous media. So if you have like stack-ups of materials in your enclosure where you have very different Z values, very different densities, the dose on the outlet of that stack-up may, or the particle spectra and fluence that transports through that stack-up may be pretty sensitive to very microscopic physics. And so in that case, you really do need Monte Carlo. Ray tracing is not going to do a good job, similar to our discussion about secondary particles. It's not going to do a good job of giving you some understanding of how nuclear reactions are occurring in your design. And then there's also the concern of anisotropic scattering. All of this is kind of getting into the idea that 3D matters. The fact that your component is situated in some enclosure where there are other components which may produce either secondary particles or scattered particles which can reach a component. All of that you need Monte Carlo to accurately model. So this is why we need both. They both kind of sit together as a complete package for doing your radiation shielding analysis. So kind of narrowing in on our improvements in 2025 R2, we have done a lot of work in the past 6 months to enable standalone transport simulations. Historically, if you wanted to do shielding analysis with Monte Carlo, you would have to do so using our normal workflow for internal charging, which requires, for the finite element, full wave electromagnetics requires a fully connected volume mesh of your geometry. In general, that type of mesh is difficult to generate for complex geometry where you may have a lot of components where the mesh elements need to connect at the interfaces between those components. Just the more bodies you have and the larger range of length scales that you have to handle in that kind of mesh, it adds a lot of constraints to the algorithm that produces that mesh. And so in general, it's very costly and often prone to failure to produce fully connected meshes for complex geometries. So in this past cycle, we've done a lot of work to provide a workflow for transport analysis that's fully decoupled from those requirements. And the way we've done that is by allowing you to basically run the geont simulation on its own. For that, you don't need a connected mesh. You simply require that you have closed surface representations of the geometry, and those are a lot easier to produce. In fact, those are produced by the software that's used to present your CAD to you on your monitor. It produces rendering facets, triangles that together form the surfaces of your geometry. Those are not generated in a connected fashion, and they don't mesh the space within the surfaces. And so simply by having access to your CAD in the software, we can take those rendering facets and use them directly as a mesh for the transport simulation. And what this means is we can do much more complex geometries than we were able to in the past for just standalone transport. You won't be able to couple this with any of our internal charging or the plasma dynamics. But for users interested in just characterizing doses and fluences in their enclosures, this really expands the types of models that you can do. To support this, historically, we've done all of our reporting for physics quantities on the finite element mesh. Because we don't have access to that, we have to have a different manner of reporting values. And so we do that with just scoring detectors attached to each body. And so the information you get out is on a per body basis. You get charge deposition, dose, fluence, with statistical uncertainty. So for the model we'll be working with today, this is kind of what these meshes might look like from the rendering facets. You do have some ability to customize those meshes, and I can show you how we do that. So I won't spend too much time on this slide. And then something we put a lot of effort into in the past month or so is allowing you to actually visualize those per body results in 3D. So it's a bit more easy for you to notice, for example, trends. And we'll go into a bit more detail on that in the live workshop part of this. So for the remainder of my time, I'm going to focus on an example analysis for that enclosure I showed. We have this enclosure. We're going to be exposing it as if it's on the exterior of a satellite in a geosynchronous orbit. This is probably not an enclosure you would want to put under those conditions for a variety of reasons. It has some pretty exaggerated vulnerabilities that we've kind of included for the purpose of showing how this analysis might be useful. Some of those things are, they're pretty large gaps in the wall of the enclosure. We've chosen a lower density plastic for the walls. And then there are these exposed connectors along this side wall of the enclosure that produce streaming paths for particles to get in, and then the connectors themselves are exposed. So for many reasons, this is not a good enclosure for putting on on the exterior of a chassis. But it's great for showing kind of the advantages of doing radiation analysis with our tool. So let's see. So I'd like to start with ray tracing. The key input for ray tracing is a dose depth curve for the given radiation environment that you're interested in. That can come from different places. For a lot of our validation work, we've pulled those curves just from tabulated data from the DSNE, which is the design specification for natural environments from NASA. Sometimes these will just come from program requirements, design requirements if you're developing a subsystem, for example. And then the thing we'd like to highlight is that you can also generate these with our SDK integration if you have some atypical orbit or atypical mission scenario that you need to generate a dose depth curve for. So there's a two-step process. One, we need a dose depth curve, and then two, we need to do the ray tracing analysis. So we're going to start with seeing how we can make a dose depth curve with Shield Plus. So I kind of have a screenshot here. I'd like to just show you in the software. So I think Well, I think I'd like to just step over to the software and show you how this works. Is SDK showing up okay on the screen share? I
Yes.
hope so. Okay, sweet. So this is Ansys SDK, if you're not familiar. It stands for Systems Toolkit. It does a lot of things, but our integration with it is very focused on being able to pull from the SEET radiation tool to get particle fluences and energies for electrons and protons for a given ephemeris. So for a very simple example, I've gone ahead and prepared a geosynchronous satellite. If I press play here, you can see it's geosynchronous because its orbit matches the period of the rotation of the Earth. And that was just prepared by just going in here. In the orbit wizard, you can just create a geosynchronous satellite. And so that's the one we're working with in this case. I did not mean to create a second satellite. And then Shield Plus is our new product that we'll be releasing. I'm not sure exactly when it's coming out, but it's within the next couple of months. And what Shield Plus provides for you within the SDK interface is these plugins that allow you to do a number of different analyses with the charge solver and the EMC Plus solver. There's this for setting up a radiation hardening problem where you have a stack up of layers. And then there are a number of others. There's a lightning strike probability workflow that I know very little about. You can actually launch a ray tracing simulation from Shield Plus. I'll be showing you that in the discovery side, but you can do that from here. And then there are there's a suite of other options that I won't go too deep into. We can also do surface charging. The one that we'll be using for dose depth curve generation is this radiation hardening button. That'll open up this panel here on the right where you can configure some parameters for that simulation. You pick the satellite that you would like to use for your ephemeris. For creating dose depth curves for ray tracing, you'll want to use the shell option. This will create concentric shells that will shoot particles through and accumulate dose in those shells. In this case, we're going to look at the geosynchronous electron contribution to dose. So I've picked electron. And I'm just going to look at a 1 day exposure, somewhat arbitrarily. And then again, for dose depth curves, we want to use aluminum. So I've chosen aluminum. And then I've set up our dose depth. You can kind of think of it as meshing for the dose depth problem. We're going to have at the outer, or I guess at the short depths of up to 1/10 of a millimeter, we're going to have 10 divisions within that. So that'll be 10 micron shells that we'll be able to get dose depth points for. And then past that, you can get away with doing much coarser divisions. And so in this case, past that first 1/10 of a millimeter, I'm going to do an extent of 100 millimeters for the full range of my dose depth curve, and I'm going to do 100 divisions within that, so 1 millimeter layers for that curve. So this is pretty straightforward to set up. If you already have some satellite that you want a dose depth curve for, it really is as simple as kind of preparing these parameters. Actually, there's one other thing I forgot to mention. There is a property within the satellite that you need to set. So if you go in the satellite, and if you have the seat module, there's one option that you need to set for the seat radiation, which is to set it to NASA. This is the AE8, AE9, or AP9, AE8, AP8 radiation environment specifications. STK13 also provides IRENE, which will give you the AE9, AP9 radiation environments. But for the analysis that was done for this workshop, I used the older models. I've actually not tested with IRENE. That'd be interesting to try. And then all that's left at this point is to click Run Workflow. So I've done that. What will happen now is it's going to open up Shield Plus on the discovery side. If we give that a couple of seconds to launch. And once that's open, it will create this geometry that we specified. It will pull in the particle spectrum for this orbit or for this satellite. And it will run a Monte Carlo transport simulation to get the dose depth profile through that concentric set of shells. Oh. It's taking a second to launch. It might not like that I have another instance of Discovery open for the second half of this. Oh, no, there it is. So yeah, I guess while that is going, I can show you, whoops, probably not from the beginning. So in the process of developing Shield Plus, we wanted to make sure we had well validated our capability for producing these curves. And so we picked two radiation environments from the NASA DSNE to do comparisons against. So on the left, we have this geosynchronous electron environment, and on the right, we have a low Earth orbit proton environment. Very different particles, different energy spectra, different fluences. And with that meshing that I showed you on the Shield Plus side, in orange here, this is the curve that we were able to produce. In blue, this is the dose depth curve that the DSNE recommends for that environment. And we compare pretty well, in particular in the range of, I guess, 5/100ths of a millimeter up through about a centimeter, which is, I think, a typical range for shielding values. And then we disagree slightly at the low depths and at the much higher depths of like a centimeter up to about 10 centimeters. I think for the most part, this is statistics. We ran this with, I think, about 10 million particle histories or maybe 100 million particle histories. And I suspect if we were to bump that up a bit, some of these disagreements at these very thin shells and very deep shells will start to kind of disappear. But other than that, we get very good agreement between ourselves and the DSNE. Let's see. So yeah, kind of as I was going through that discussion, Shield Plus has opened up. When you launch it, it will warn you. You can just go ahead and click through. And what's going to do now is generate all of those shells, assign them to be aluminum, and then start a dose depth simulation. In the interest of time, I'm not going to let that simulation run. It typically takes 1 to 2 hours to complete the analysis for that. That a moment. Okay. So you can see it really is as simple as setting up a bunch of concentric shells. Big, it looks like a big sphere. It's doing a lot of processing at the moment because there's a lot of bodies in this model. Oop, just give it a moment. I guess there's not much to discuss while we're waiting for this. In the interest of time, I might just jump over to ray tracing because we have about half an hour left. So assuming you let that simulation fully run its course, you'll have a dose depth curve, which you can now use as an input for ray tracing. So I have this model, showed it previously in the slides, but this is an enclosure. It has an aluminum lid, has a plastic wall that we'll be applying. And then if I go ahead and hide some of this geometry, we can look at some of the internals. Yeah, so there's a number of, an array of transistors here on the top board as well as on the bottom board. We have in here a chip inside of kind of a box for shielding. Now on top of that, we have a tungsten layer to provide additional shielding for that sensitive component. Then, a number of other components here that may be present in the design just coming from your mechanical team. I previously highlighted for some of these vulnerabilities, for example, these holes here on the sides, as well as if we click over to the right side, we have these connector ports that, if you kind of zoom in, you can see there are some substantial gaps here that can provide streaming paths for radiation to come in, and then these connectors themselves being exposed is somewhat problematic. And I've already gone ahead and assigned materials for this model. I'll show you how to do that for a few of the bodies, but if we go through and look with inspect materials, we can see some of the materials I've been assigned. I mentioned, I guess it's lead, not tungsten, sorry. I've assigned lead to this thin patch on top of this kind of box on this chip for shielding. There's polyimide on the boards, stainless steel on some of these fasteners. And then most of these components are just, I've set them to be silicon. To assign materials in charge, what you do is you come in here and you can create a new body material. So for example, should bring back the lid. If I wanted to assign aluminum to some of these components, I can go into our material library and select aluminum. If you have materials that are not present in the library, you can come in here and enter for both the transport and the ray tracing analyses. The only parameters that really matter are the atomic mass, atomic number, and densities. And so I have aluminum present here. I can go ahead and assign it to some of these aspects of the enclosure. It's as simple as just clicking on them once you're in this tool. And then to save changes, you just click the check mark. Yeah, I went through that process ahead of time because for this many components, it takes a little bit of time. For ray tracing, the only thing that you really need to do then is to go ahead and assign detectors. So I can go ahead and hide this lid again so we can see some of the components again. And I'm also going to hide the walls. And I'm also going to hide these boards just so that's a bit easier to see what we're doing. Good. And then I've already gone ahead and selected a few of these components that we'd like to do comparisons for. So I'll create detectors for those. Everything for ray tracing is going to be controlled on the charge side through this button and its corresponding dropdown. You can create materials here, as well as assign detectors. For ray tracing, the way that we handle ray tracing is when you select geometry for your probe, we create a tessellation of that surface of that geometry and do ray tracing from all of the points in that tessellation. And so it's very straightforward to create samplings over an entire device, for example. You'll see here on the left of the tool, we have a body selection mode and a surface selection mode. I think most people will want to use this body selection mode. The way it works is you really just come in here and you click on the bodies you would like to create samplings for. Actually, did not mean to do that one. I'm going to work through the ones that had pre-selected. So I'm going to pick kind of some transistors on both the top and bottom boards at the ends of the arrays. I'm very interested in this chip, which has a lot of additional shielding just for it. So I'll click on that guy. And then just to round things out, there's a couple of other chips that I selected as well. So I'll hit the check mark. And we've gone ahead and created probes for all of those. When we go to do ray tracing, again, like I said, we'll create a sampling over all of the surfaces of those bodies, and we'll do ray tracing from them. Some other thing that you can do is actually use the CAD tools in Discovery. So I might actually bring this back in for a moment. Not that. Never mind. I wanted the walls back, but I think I can do this anyway. If we kind of zoom in, I mentioned those holes kind of in the corners of the enclosure. I'm interested in kind of what dose is in the vicinity of those holes. And so I can go ahead and create a surface detector. I'm just going to use one of these planes just out of convenience to kind of sketch on. Rotation, if that's kind of weird. There we go. And I'll just prepare kind of a rectangular. Oh, this is strange. It's rotated in a way I wasn't expecting. Maybe I'll try this differently. Maybe easier if I bring this back. Is this what I want? Is this what I want? There we go. Yeah, I wanted the walls here. Yeah, there we go. So as I was saying, I'd like to do kind of a just sampling in the vicinity of these holes to see to what extent it enhances dose in the neighborhood of it. And I think in the interest of time, I'm just going to do one of these. In the slides, I'll present a couple of additional ones on both sides of the enclosure, and then I also prepare one kind of in the plane of one of these ports, and we'll look at those results when we go back to the slides. Oh, I didn't mean to extrude that. I meant to move it. I'll just move that a little bit offset from the geometry. And then if I go back to the probe tool, in the surface mode, I can go ahead and just select this surface and assign a detector to it. And it will just go ahead and, just the same as the surfaces of those volumes, it will create a sampling across that surface and give you a nice dose map over that surface. For ray tracing, that's really it. At this point, we can now go ahead and click into the ray tracing control. We can set a couple of the main options. The main parameter here is just the number of rays you'd like to sample for each point in your tessellations. I'll just leave it at the default. And then you can import your dose depth curve. Now, just to show you what that file looks like. These files will be prepared automatically for you if you run things through Shield Plus, but if you're pulling these in from other sources, it is just a 2-column file of depths in aluminum in meters, and then dose in rads. If you have some other quantity that you're doing ray tracing for, just express it in those units. So these are pretty straightforward to prepare. This is one taken directly from the DSNE. I also have one that was produced with Shield Plus here for the geo environment. And in this case, we produced a much greater sampling and depth. I did the testing with the DSNE dose depth curves, so I'm going to stick with that. And then for ray tracing, we just click go. I will actually let this run through because this analysis will only take 1 or 2 minutes. So as we kind of discussed, this ray tracing is being performed on the GPU with an NVIDIA framework using NVIDIA hardware. And so we're able to trace a very large number of rays every second. I think this one ends up being on the order of like 100 million rays, and we should expect this to take about a minute or 2. So while this analysis is running, we can kind of see some output from the solver. It's already finished one of those surface tessellations, and it's moving on to the next one. And this will just kind of chug through. And while that's running, we can take a look at some of the files that generate with the simulation. You'll get some of these files associated with the actual surface visualization that we'll look at in a moment when the simulation is done. We generate these tracks files for all of the least shielded rays, and we do this on a per detector basis. And I'll show you what those look like as well. And then probably of most interest for most cases is this full report file. For each of the detectors that you create, we'll output some information that might be useful. We output some information about the least shielded rays that were identified and the shielding thickness along them, what that is in equivalent aluminum thickness, what the dose is from that ray. And probably the most useful value is this dose estimate at the end. This is just a average of all of the points on that detector. And so this is the value that you'd use to most closely compare with, for example, a Monte Carlo analysis. This is probably pretty close to done. Trying to think if there's anything else I can show you in the meantime. Let's see. No, probably just give it a moment. Maybe there's something in the slides I can show. Yeah, I'd much rather show this in the UI. Let's see. So I guess in the time that this has been running, we can get an estimate of how many rays. Looks like so far we've done 15,000 points, 20,000 rays per point. So it's about 300 million rays so far. I think this is the last one. Nope. Okay. I guess I'll let this run in the background, just in the interest of time. There are some things I'll be able to show you once that's finished, but we do have some screenshots. So I mentioned you can create some of these surface probes kind of anywhere you want. For the work that I did prior to this workshop, I prepared some on both sides near those gaps, and you can see that there's some pretty significant dose enhancement kind of in the neighborhood of those gaps, much greater than anything that you'd see on the individual components. And then similarly, you see the same thing kind of near this enclosure port. Something else I'll be able to show you is our track rendering. So something that we also output from ray tracing is all of the least shielded rays from a given detector. And then you can pull those into Discovery to take a look at them and see where your vulnerabilities are in terms of shielding thickness. And so in this case, it's pretty exaggerated because we have this detector right next to just holes. And all of those least shielded rays are going straight through those gaps. And so for this exaggerated case, it helps you find kind of ports or gaps, but in less exaggerated cases, it can help you identify where it might be useful to add patches of shielding, for example. And I can show you how to do that as well. This is what the rendering will end up looking like in just a moment when we're done. You can see we get much higher dose on this bottom array of transistors than we do on the top. And then it seems like our shielding has accomplished what we wanted for this chip underneath this lead shielding patch. Okay, yeah, ray tracing is done. You can tell because it says ray tracing completed and it says check-in succeeded. So once the ray tracing analysis is finished, you'll get this this node down here in the tree that allows you to do 3D surface visualization of your results, and you can see these surface maps. I had the transport results preloaded. So yeah, like I said, you get this significant enhancement of dose near the gaps in the enclosure. So much so that it completely washes out the color scale for the other parts, so we'll have to adjust that. We'll bring this down to about 600 rads. And we can start to see kind of the same observations I showed in the slides. These transistors on the top board are seeing much lower dose than their kind of cousins on the bottom board. And this is just because, well, one, the walls of this enclosure were arbitrarily set to be a lower density of PTFE material. And then also, these transistors on the top are shielded from below by 2 boards instead of 1. And so just in general, they're much better shielded than these transistors. You'll see also the, we'll actually reduce this color scale even more to exaggerate. Most of the dose that's being deposited on this chip is actually just these sides that are not shielded compared to the top surface. Somewhat interesting. And yeah, in the interest of time, I'm going to move on to the transport results. So yeah. So yeah, complementary to our ray tracing option, you can also do Monte Carlo transport to get a more high fidelity picture of dose deposition in your parts. The setup for this is very similar. You create your material definitions for your CAD. And then really most of the work then is just defining your particle source. And then the conditions of your radiation, and then maybe some of the additional transport physics parameters. That's just going straight back over to Discovery to set that up. I'll go ahead and delete this surface because we don't need it anymore. And bring back the full geometry. Because all the materials have been assigned already, all we need to do is set up our particle source. You have a lot of options for setting up particle sources in Charge. For this workshop, we have a geo-electron example already built in that you can set up. So if I just click that, it will create for me a geosynchronous orbit electron environment. And that's specified by the integral energy spectrum of the particles and fluence. This is pulled, I think, just directly from the DSNE as well. Yeah. Important for this analysis is that we're in an isotropic radiation environment, and so we'd like to mimic that with the geometry of our source. You have a number of options depending on kind of the conditions of your problem, but for a space radiation environment, you want an isotropic source, and so we'll choose spherical, which will create a spherical source surface for the transport that completely encloses our geometry, and then choose an isotropic incidence, so an isotropic angular distribution for particles generated from that spherical surface. And then we want to run a single time step for transport. And then the last thing you want to control is statistics. So we've mentioned Monte Carlo is a statistical method. One of the main lever that you have for improving the convergence of your results is to increase statistics. For something like this, where we have relatively small features we would like to accumulate dose in, you need relatively high statistics. And so before this workshop, I ran this simulation already with 1 billion particle histories. That was run on my desktop. I ran it on 4 cores, and that took about 40 hours. So if you have more compute resources to throw at it, you could definitely pretty easily push much higher particle counts. But just for demonstration, I stuck at 1 billion. And really, that's all that you need to do. If you have other particle spectra that you'd like to define, you have the ability to actually import directly from SDK if you have some satellite already defined. Just the same as we pulled the particle spectra for the dose depth curve creation, we'll do the same thing for importing a particle source for transport. It actually uses that exact same capability, the dose depth curve, and then just general simulation. And you just tell it the name of the satellite, and then it's kind of that simple. I won't do that in this case, just in the interest of kind of keeping to the original demo material. So yeah, in general, you can import any kind of spectrum if you have it expressed as an integral spectrum or a differential spectrum. If it's integral, then you'll specify it with the manual option and enter them into this table. If you have a differential spectrum, you can actually prepare an input file and just import it here. So yeah, in the interest of time, I'm going to move on, but you have a lot of customizability with your particle sources, and you can also mix particle sources. So if you have a mixed radiation environment, say you have electrons and protons, I can come in here and add, one of our many options: electrons, positrons, alphas. If you have a proton environment you'd also like to add in, it'd be as simple as creating it here. But just for demonstration, I'll stick with just the electron. There's some options you'd like to set in the domain as well for radiation hardening. So for this standalone decoupled option that we've been discussing today, all of that is controlled within the radiation hardening simulation type. And there's only a few parameters for that. You give it an irradiation time, very straightforwardly. And then you have a couple of options for the GEONT simulation. The main one you might tweak is your physics list selection. GEONT provides a number of different, for example, EM physics lists that do a better job of handling low energy electrons and photons and so forth. And then if you have hadrons, so like ions or neutrons, where nuclear reactions and nuclear scattering are very important, you'd want to use this FTFP Bertini cascade physics list. But we're working with electrons, so we'll stick with the electron physics list. I had discussed the meshing for the standalone transport. You have kind of two surface mesh options. One would be facets, where we just take the rendering facets and directly use that as a mesh. This is going to work relatively quickly because these facets are already generated just to produce this rendering that you're seeing right now. And so I tend to favor it for that reason. We also have the option to use the built-in Discovery Artemis meshing. And so this is just using Ansys's meshing options to produce a surface mesh. And just the same, you can use that for standalone transport. For the demo, I use the facets because they're quicker. I think I actually already have the mesh loaded, so I won't go ahead and wait for it to mesh. Come over here. There we go. Yeah, so this is what that mesh ends up looking like for this geometry. Again, yeah, in the interest of time, I'm not going to go too deep into it, but kind of give you an idea of what kind of mesh you can expect to get. You can actually use this cut plane option to look inside of the geometry and see what the mesh looks like on each of those components. And we may take a look at that when we look at the results. So to recap, we had to assign materials, we defined our particle source, we chose our meshing option and irradiation time, and that's really all that you need to do for the standalone transport simulation. At this point, what I would do is click Start, which would launch a simulation that would run for 40 hours. And so I won't make you sit through that. Instead, I'll just show you what the results of that simulation look like, which I already have loaded. So what we do is construct this rendering, a color scaled rendering of your probe results. You can actually use this cut plane to kind of look inside and see the dose and various quantities on each of your components. The rendering is a little slow to update just because there's a lot of mesh elements here. So maybe if I rotate this about 90 degrees. Oh, I think I was selecting the wrong thing there. Okay, well, in either case, I have some screenshots I can show. But there are a number of quantities that you get out of transport. We'll show you not just your dose, fluence, charge, and energy. But we'll also show you the statistical uncertainty that was accumulated in each probe. So for example, I can look at the uncertainty in my dose and just give that a second to update. And we can see kind of a heat map of where our uncertainty is highest in the geometry. So for example, it's pretty quick to identify that some of these smaller components and some of these pins are as high as 60% uncertainty with the statistics that we accumulated. And this helps you find, help you identify for components which you care about, did we get enough statistics to be well converged and thus to make good conclusions. Anyway, I'm going to move back to the PowerPoint just to show some screenshots for this. I'm going to skip past this just for the moment. So this is what the rendering, the visualization will end up looking like for your scoring results for this demo. You'll see, in this case, I'm showing dose. I guess I'll expand that. And then there's some similar conclusions that you see from these results that you saw with the ray tracing. For example, it's very evident that this top row of transistors received a lower dose than the bottom row. You'll see that this chip underneath this cage also was pretty successfully shielded by that lead layer that we added, and kind of so on. I wanted to show a quick comparison between the Monte Carlo results and the ray tracing results, just to kind of show apples to apples. And so I selected those 11 components that I put ray tracing probes on. We're going to do a comparison between the ray tracing dose and the Monte Carlo. This is just kind of a simple table. We see part A is that chip that's kind of underneath that lead patch. Kind of pretty comparable results, 45 rad, 33 rad between ray tracing and Monte Carlo. These two chips, they're very similar parts, just on the top and bottom boards. Pretty consistent dose between ray tracing and Monte Carlo, especially the relationship between the two parts. And then these arrays of transistors, we see, D1. So the indices D1 through D4 are counting from left to right along the row. We see decent agreement. We have relatively large error bars from the Monte Carlo for these components, and this is just because they're pretty small. And so smaller features tend to have fewer particles track through them from the Monte Carlo, and will be sensitive to kind of higher uncertainties than you might, or they'll be your limiting cases for uncertainty. So in this case, we were saying up to like 20 to 25% just running a billion particle histories, which may indicate a need to kind of refine our statistics. But in either case, there's still some interesting trends. We can see that both the ray tracing and the Monte Carlo agreed on the fact that the top row of transistors and the bottom row, there's a pretty significant difference in dose between those two cases, and roughly a factor of 2 between them. And so kind of as I was alluding to, this is a mistake on the slide. This should be 1 billion, not 500 million. But we still have significant statistical uncertainty in some of these parts. In the worst case, 20 to 30%, which is, I think, too large of an error bar to make very strong statements about, make strong conclusions. So what could we do at that point? It's not a trick question at all. We should just run it with higher statistics. And kind of to give you a rule of thumb for how many statistics to add to achieve some target uncertainty, you can make a pretty accurate prediction of how increasing statistics by some factor should reduce your uncertainty. It should reduce the uncertainty by the square root of the factor that you increase by. So in this case, if I want to achieve less than 10% uncertainty for my worst case volume, which was D3, I need to improve by roughly a factor of 3. And so I need to refine by about a factor of 10. So instead of running a billion statistics, I need 10 billion, which is pretty feasible if I just, give it more cores on my desktop and let it run a little bit longer. It's kind of the decision-making process that you would make here. So yeah, I think that is the last slide I had. Oh, upcoming things to look out for. Over the next 6 to 12 months, we have a lot of exciting things coming down the pipeline that we want to develop for our radiation hardening. One is we want to bring in some packages for doing single event rate predictions, and also some physics lists for doing GPU accelerated electromagnetic physics. And then there's some improvements we'd like to make to our scoring volumes. We'd like to add some more quantities. And then kind of one thing you may have noticed with the scoring volume visualization for the transport is that for that workflow, we attach those probes to every single body, which is fine. It doesn't really impact runtime, but it can make it a bit tedious to visualize because, for example, the enclosure is included in that rendering and can make it hard to occlude and see some of the components. And so we'd like to give you a bit more control over that. So those are kind of the things to look out for, not in this release, but in kind of upcoming releases, some exciting stuff that we have coming. And with that, I think we're just at exactly an hour and a half. So I'll kind of get back the time for questions and answers. Then I can also show things in the UI if people are interested in seeing how to do certain things.
Sounds good. Thank you, Colin. Maybe we can take some time now to go through questions, and then if we get through them all, we can look back at the UI while people think of more. The first question that we had, I'll read it out and either of you, I suppose, can answer. I think I heard a comment that the PIC solver can help with analyzing degassing. If that is correct, can one analyze how the internal pressure of a module or nested arrangement of modules changes as a function of time once exposed to a vacuum environment?
I'll probably give that one to Kevin to answer.
Let me reread that.
Certainly, yeah. I think I heard a comment that the PIC solver can help with analyzing degassing.
Yes.
If that is correct, can one analyze how the internal pressure of a module or nested arrangement of modules changes as a function of time once exposed to a vacuum environment?
Yes.
Cool.
They're very simple answers, but yes, we monitor the density. We know the volume of the gas. We know the temperature of the species. We can get you the pressure from the typical laws, and then that will be something we can do. Yeah, the advantage here with PIC is that we're really not bound by any loss in continuum at the interface with the vacuum. So you just let it kind of diffuse into the vacuum over time. Any particles, doesn't have to be charged particles. The PIC particle is tied into our electromagnetic solver for charged particles where we calculate space charged and such, but it can also be used just for neutral particles.
And of course, for any of these, feel free to post more follow-ups in the chat. The next question was, why is the gamma ray option not directly available in Charge Plus? And can we use high energy photons instead?
For the particle transport, the label in the particle source tool is photon, but the particle type that's written for the the GEONT simulation is the gamma. So the answer is if you choose this photon option, it will be using the gamma particle type in GEONT. And so yes, you can do high energy gammas for your transport simulations.
Our next question, why does the TID increase for gamma rays for thin materials as thickness increases while simulating in Charge Plus?
That's a great question. And there's two possible answers. For the curve that I showed in the PowerPoint, so if I go back to that, I'm assuming it's asking about kind of these trends up through the first 100, or I guess 10 microns for both the LEO and the LEO proton and geo electron environments. And there is a small increase. There's two possibilities. One is statistical. These are really thin shells, and we may just have relatively high uncertainty in those shells that makes it appear as if the dose is increasing. I think there's actually a physical explanation, though, that's a bit more likely, which is that there is, and this is just something that you see, it's dependent on particle type and energy. You'll see actually buildup of dose over very short extensive shielding. Um, um, and this is something you learn about if you take like a health physics class or a radiation shielding physics class. I learned about this in university. Is that over that short range, you start to produce, for example, these electrons as they collide at just the surface, they're going to pretty quickly start producing a large amount of secondary photons, which will transport a short distance and deposit energy. And so it's very common, especially for charged particles, to actually see that very short range increase in dose. I don't know if that's exactly what we're capturing in these plots. I don't know if this is the correct buildup range for this energy spectrum, but there is a possibility that that is explained with physics. I hope that answers the question.
Next, we have what default value should we select for photon flux and number of particles for a particular time step, especially for photons?
I mean, it depends on your radiation environment. If you have kind of general interest in like dose per unit fluence, for example, in your design. So if you want to be agnostic to fluence, you can just set a value of 1, and then scale it, scale the doses that you get out, and so on, by the actual fluence of your radiation environment. It's a hard question to answer because there's a pretty large range of radiation environments your design might be exposed to if it's sitting in like a photon pulse facility. It'll have a very different characteristic fluence than if it's sitting in some other context. And so, yeah, I guess it depends on what kind of problems you're interested in, would be my answer.
Next, we have which should be selected between global mesh or extrude for rad-hard simulations?
That's a good question as well. I'll bring up the UI. So for the rad-hard workflow, extrusion meshing is a pretty particular case. If you have some CAD like this that you'd like to import, you'll just want to use the normal meshing. You will not want to use extrusion. So in that case, you would just use the global settings and pick either facets or discovery 2D. Or if you're doing internal charging for this kind of model, you'd want to use either discovery or a legacy option. Extrusion is for cases where you have how do I explain? It's ideal for cases like if you're simulating the dynamics of a cable in charge, where you have some cross section and you'd like to create hexahedral elements along the length of like a cable. And so there's very particular geometries that you'd want to use extrusion for. But for general applications like this type of analysis, you'd want to just use kind of the default settings.
Thanks, Colin. Next, we have how does the STK integration handle lunar orbits or lunar surface environments where there are no trapped particles and the effects are primarily from SEP/GCR?
Oh, that's a good question. This is something Kevin and I were discussing earlier. At the moment, I think our STK integration in the current builds of the software will only pull in electron and proton environments. And so I think currently the STK integration does not pull in like the galactic cosmic rays and so on. I am unsure of whether SDK provides those environments. So maybe in the future, this is something that we could look to integrate. It would be necessary for some of the other capabilities that we've been talking about, like the single event effects. I don't know if Kevin, if you had anything to add there. I'm not super involved with our SDK integration.
Well, it's more about the models that exist, right? There isn't enough data beyond geo to complete those models and have proton and electron fluxes. Um, so what we have are worst case scenarios from the standards, but we don't have like mission dependent databases like we do for everything up to geo with Irene and AE8, AP8. So at that point, we have to leverage the integral fluxes from the standards.
Makes sense.
Next, we have, is it possible to add a custom material or complex material, including composition ratio of different materials?
Yes, I have a slide on that I skipped over. So because we are a wrapper for Geont, you are able to define materials and kind of the typical syntax for Geont. And there are a lot of materials out there that you can find from CERN on the syntax for those things. At the moment, there's no UI support for creating composites, but you can easily create them by going into your exported GDML, which is the input file that Geont uses for configuring the transport simulation, and add in composites. So in this case, actually for the simulation that was run for this demo, there are some stainless steel components that I included, and I created a stainless steel material in that input file. And the syntax is pretty straightforward. It's probably it's very similar kind of setup to what you would do in something like MCMP, for example, where you declare the Z number that you'd like to include, and you can give it a label, and then that can be used for either mass or number fractions for creating a composite. It just requires some manual editing of your input file, but it's not too difficult to do.
Could you elaborate on the planned SCU rate predictions?
There's it's very early stages for the SEU stuff. We've done a lot of literature review and assessment of packages that already exist for Geont-based applications. And there are tools that are out there, open source tools that allow you to, for example, if you have some input for a single event cross section for your component, combine that with fluences from a transport simulation to produce single event rates. That's kind of at the highest level that you could do that type of analysis. There is additional complexity that we're considering doing research and development for. That without getting too deep into it would be aimed at not just you provide us cross sections and we give you rates, but trying to provide some simulation-based solution for producing those cross sections, so that they aren't something that you have to produce, for example, from testing, from destructive testing. So there's kind of that's about the level of detail I can go into at the moment. But yeah, the kind of the first stage is bringing in some of the existing Geont-based applications and packages for doing this type of analysis and making it accessible and easy to configure with our UI and our CAD handling and all of that.
Can you please comment on when the ray tracing and Monte Carlo dose calculation results may differ more?
Yeah, that's a great question. I think we had some discussion of it earlier, so I can go back to that slide. Yeah. So why might they differ? There's a lot of reasons. I think in extreme energy ranges, so that could be very low energy and potentially even very high energy. I'm a bit skeptical about ray tracing providing a good estimate, because in those cases, you're going to have a lot of impact to dose contribution from second order effects. So things like a particle comes into your design, produces a secondary particle by interacting with some component way over there that then transports over and deposits dose in this component, right? Ray tracing cannot give you any handling for that type of effect. And depending on your particle species and depending on energy of your environment, that might be a pretty significant contribution to dose. These like secondary scatterings and then also generated secondary particles. Monte Carlo is going to give you very different results if nuclear reactions are a very important part of your concern. So if you have certain heavy ions or galactic cosmic rays, kind of the doses you get from that are going to be very dependent on not just the nuclear reactions occurring at the deposition site, but again, as I've been hammering on, they'll produce secondaries at other places, and the kind of trajectories of those particles being generated elsewhere and depositing in my component, you really can only get that from Monte Carlo. And so those types of cases are where they'll probably significantly differ. Ray tracing will be a lot closer, and in the kind of case that we demonstrated today, which is you have kind of a middling energy spectrum of charged particles like electrons, where when they irradiate your design, they're going to slow down over a pretty short depth, and then create a lot of photons isotropically. Cases like this, you should expect to get pretty good agreement between ray tracing and Monte Carlo. But yeah, depending on geometry, depending on particle species and energy, that's when they can start to differ significantly. In that case, I would rely on transport much more so than ray tracing, just to be clear, because it's giving the accurate physics.
Does more TID mean more penetration of rays?
For the ray tracing solver, more TID from ray tracing means that there was a less average thickness when we were looking in all directions from your component. And so yeah, that will, from the physics perspective, can correspond to more penetration, less attenuation of the incident radiation.
How accurate is particle tracking, as every time it shows photons penetrating?
I'm not sure how accurate. Is this the particle tracking in the charge UI, like the tracks that we generate? Not. Yes, I'd ask for clarification, I guess.
Yeah, please feel free to add a comment under that question to clarify. Our next question is, in comparison in percent, you have shown in the slide which environment, like GEO, NRHO, or is it something different from DSNE you have used?
For the workshop material that we showed today, we used the DSNE geosynchronous electron environment. And so the reference for that is here. The DSNE. Oh, sorry.
I think there's a misunderstanding of the results you presented. The percentage that you're presenting is not a percent difference between
I see.
Monte Carlo and ray tracing. It's a percent error on the Monte Carlo result based on actual physics and statistics.
Yes. Yeah, so these uncertainties, yeah, as Kevin said in this table, they're not percent differences. These are for the Monte Carlo simulation. Depending on the number of simulated particles are deposited in any given body, we can calculate a statistical uncertainty in the quantity that we report. So it is, here's a reported value and our uncertainty. So yeah.
Do we require a separate SDK plugin for Shield Plus?
Yeah, Shield Plus is an installer, a separate installer for STK. It's a plugin.
Has the mesh engine changed in this demo version from 25R1? When I've tried to run a similar case to the STK shell demo, I was getting mesh errors when trying to model a thin layer with many layers. Is this easier / more robust in this upcoming version?
Yeah, I think some of the new meshing options that we developed for the decoupled transport will make those kinds of cases much more consistent to mesh. And so if you're having difficulty in 25R1, I would give it a try in 25R2 and see if you have more success for sure.
The bulk of the issue comes from the fact that in 25R1, we were requiring volumetric elements to be generated. And this new meshing workflows allows you to only save and use surface elements to solve the rad-hard problem, which makes it for an easier thing to mesh, especially when geometry is intricate and layers are thin, etc.
Those are all the questions that we have for now. Colin, if you had more UI content you wanted to go through, I think you can feel free to use our last few minutes doing that. And if anyone has remaining questions, can feel free to continue posting.
Oh, is there anything you would think would be good to show, Kevin? I don't think I had much more prepared.
No, I think we're good to go. This is a good conclusion to the session.
Sounds great. Well, to answer the last question that we just got in the Q&A, after today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. If you have questions about a particular section of interest to you, please feel free to reach out either through the ema3d.com website or via email. Next up in our Expo series, look forward to Introduction to Space Environment Effects, another no-cost virtual event, including several training workshops and technical discussions, which will begin, I believe it's this afternoon. So you can look on our website for that registration. Thank you all for your time and attention, and have a great rest of your day.